something else. This is binary data, and binary data is not text data. So there's a very decisive difference there. And Linux programs should use text as a universal interface such that we can read this text, we as humans, and also this is like a baseline for this approach to work out pretty well. So one process pipes its output as input to another process, and we discussed this and saw some examples. This was the first task. We did an assignment standard streams there, and I guess there is some homework left, if I'm correct. Yes. So we did the file redirects with this quote from Abraham Lincoln in its speech at Gettysburg. And there were two parts left. I will show them to you. Addressing the first one, redirect and save, where the task is to read about the T manual, because the T manual does exactly what the T says, not the T. I'm actually drinking tea right now, so I don't know if you see it. It's not tea, the beverage. It's tea like the letter T, and the functioning is similar to a T, because I show this to you. Let me log into my virtual machine. So, oops. If you have, for example, a command that was mentioned in the task DH and the option H, this means, or the output of this command is, you see it, or some data about your hard drive and your file system. So you see the file system that is at the root directory here is 33% in use because it's not big. So we have 24 gigs in there. I used already 19 gigs. So I need to act pretty soon. But this is just a virtual machine. Anyhow, the output of the command is not the important thing. What you can do is you can pipe this output into T. And what T does is it creates like a junction in outputs. It takes the standard input stream and writes the standard input stream into a file that is passed as the first argument. So for example, disk usage, txt. And as a second feature, it pipes through all what comes in from the standard input stream and passes it to the standard output stream. So T does both. It passes through standard input to standard output, and it writes standard input to a disk. Whereas cat, for example, we had that the previous time, the last time, cat does just pass through standard in to standard out if you do not provide an argument. And T does both. So this is the key difference between T and cat. So when we execute this, we get an actual output because standard input is passed through standard output. And if we cat disk usage.txt, I'm expecting that we see the same that we have seen in the shell here. Yes, so the file is not empty. The file exists and it is not empty because standard input was also written and redirected to this disk. So this is basically what T does. We have talked about less before, so we skip this. And we proceed to part 3, the pipes. There is a document attached, Frankenstein.txt, which is Mary Shelley's novel that hopefully some of you know. And the task is to count the instances of Frankenstein within Frankenstein.txt. And this is a very good example where pipes really shine. So in text processing, piping and the small utilities that we use, and if we chain them together in a suitable way, then we can achieve rather complex tasks easily. And one example is counting words in a document. So let's see. Let me clear my shell. I have Frankenstein.txt there. We can take a look at Frankenstein.txt with less. There you see It's Frankenstein from Mary Shelley. And you can read it if you have enough time. But I guess as a student of artificial intelligence, free time is rare these days. But anyhow, so this is the novel, and it's quite long. And we can count the lines, for example. So in this task, you need to apply the grep command, plus you need to apply the WC command. So be aware, WC, this is an abbreviation in Germany for the toilet. So this is typically abbreviated if you go to the airport, for example, and you see a sign that has a WC on it. This is basically the toilet. But WC in this context does not mean toilet, it means word count. So you can count words and lines using this tool. And if I kept not favorite.txt, but Frankenstein.txt, typo, and type it into the word count command, you see three outputs. The first one is the number of lines in the file. The second one is the number of words in the file. And the last one is the number of bytes of the file. And we can verify this pretty easily, because if we do an ls-la, we know this is the long format of the ls command. We see the match. We have a match here for the number of bytes of this file. So this is word count, this is line count, this is byte count. Okay, so how can we now count lines or occurrences of Frankenstein.txt? Let's start with, clear again, catting Frankenstein into the grep command, because the grep command is the command that can filter. And if we filter for Frankenstein, then the output is as this. So the output is not the whole novel anymore. What grep does is it applies a filter and only outputs lines that match the argument that you provide to grep. So these are all the lines that include Frankenstein.txt. We can count them by piping this into WC in word count. And if we want to count the line, we can provide the option -l. And this gives a count of 30. So the question is 30 the right answer? By coincidence, yes. But what you did here is you grepped for Frankenstein.txt, and you need to understand that Frankenstein.txt, that Frankenstein.txt greps for lines, right? So you get lines back from grep. So if you do word counting on them, this 292 is the wrong answer, because you count words that are in the line where grep found a match for Frankenstein. So this number is wrong, and we need to work on our command a little bit better. I mean, by coincidence, or is it? I guess it's 32. It's 30 or 32. Let's see. So with this, we need to be careful, because there might be lines that have two occurrences of Frankenstein on the same line. And what we do here is line counting. So we might miss these occurrences. And what we also want to do is we want to get rid of all the surrounding text in a line. And if you read the manual of grep or consulted the internet otherwise, you should discover the -o option, which only prints out the occurrences of the matching phrase. And now we see all the surroundings of the lines are gone, and we only have the occurrences of Frankenstein. Now we can do the line count and have an occurrence there, and we get a number of 30. There is still something that we need to care about, and this is if it's a capital or like cases of characters. I guess one occurrence is there that has only caps. So let's read about the manual of grep and see an option where we can ignore the case. So look at that. -I ignores the case. So let's enable that. So we enable option O, we enable option I. Yes. And now we have 32 occurrences of Frankenstein. If you remove the word count, you see the last one, it's a whole caps Frankenstein, and the third one is as well all in capital letters. So the correct answer for this question is 32. The most important aspects of this task is you need to filter, you need a word count. Technically, you don't need the cat because you can use grep with a file name as well. Frankenstein. What is the syntax here? Is it this way? Yes. So you can provide, instead of piping the input from standard input, you can tell grep to read the input from a file, which is frankenstein.txt. But yeah, for the sake of showing how pipes work, I used cat here. Yeah, other challenges were reading about grep and finding -O and -I, and reading about the word count and using the words with -L or the lines with -N. Does anyone have a question? What does, is it my screen is very small, -L mean? You mean in the word count? So typically the output of WC is this, right? So you have a triple. The first one is words, the second one is lines, and the last one is bytes. If you just want to have the line count, you enable -L. If you just want the word count, you do -W. And actually, I don't know the filter for byte count, it's -C. So if you do -C, you get the byte count, right? So instead of outputting a triple, you get the numbers that you like. Yeah. No further questions? Then, so this was, we are still in the recap. This was our discussion on streams. Then we discussed users and groups. And users and groups are important because file permissions are based on this. Yeah, here we have the output here. So every file or directory has assigned an owner in a group. And what you see here are the permissions that specify who can do what on this file. And this is two-dimensional. The first thing that we need to understand is ownership. So every file has an owner, which is a user account, and every file is associated to a group. And a group can include multiple group members. And this is suitable for scenarios where you want to assign a permission to a group of users. And the method or the way how you can achieve this is using groups. And world is the complement. So world are all users that are not in the group assigned to a file and are not the owner user account of the file. So this is basically the rest. And you can assign permissions to these three categories. You can assign permissions to the owner, you can assign permissions to the group, and you can assign the permissions to the world with read, write, and execute. Read grants read access, write allows modification, execute provides execution rights for a file, because we need to include binary files or programs as well, because programs are files on a disk. And in order for a user to execute a program, this file that holds the program needs to have the execute flag set. And this applies also for scripts. We will talk about scripts today. And we saw the commands with change own and change mod, how to set ownership, group associations, and file permissions. And then we saw some groups, some commands where we can add a user, add a group, and add a user to a group. And as far as I remember, and my notes are correct, we stopped right here. And we complete the task users and groups right now. So this is what we do right now. So let me switch over to my file browser here. And we do the first two. We do privilege delegation and we do users and groups. We do this in two parts. So for privilege delegation, this is the concept of sudo. I give you 10 minutes, and for users and groups, I give you 10 minutes as well. 10 minutes as well. And we do our breakout rooms again. So let me create the breakout rooms. I mean, you can give me feedback. So this was a feedback from the last term. And their students said they like the breakout rooms because they can collaborate with peers and have like a discussion on the topic without like the professor taking place of the discussion. So please give me a green check mark if you like these breakout rooms and give me a red cross if you think this is not a good idea. Oh, that's close. Okay. Yeah, thank you for the feedback. Although the red crosses have a slight majority, we do the breakout rooms because I think this is something that where you learn and it activates you and gets you up from like sleeping. So let me create the breakout rooms real quick. Breakout rooms there, recreate all rooms, 4 to 5 people equals 12 rooms, assign automatically, created, and yeah, yeah, let's do a 10-minute sprint for privilege delegation and try to do privilege delegation in 10 minutes. Then I will show you the solution for this. And then we do users and groups using the same breakout rooms. So I will open the rooms right now and you work on part 1. Let's go. You can join now. So let's wait until the breakout rooms close and everyone is in the main room again. Marco in the file. This is a task, but you will see, or if I guess you have experienced it, that this is not as trivial as it sounds. So let's see. So I'm in my terminal emulator again. I'm switching to the op directory and I'm creating make dir. This is the command that I use for making a directory shared, and it does not work. Why does it not work? You see it directly here. You see this line? This is just a single dot, right? And these are double dots. These two entries in the output of ls-lah mean the following. So a single dot means that this is, or these are the permissions, and the ownership/group assignments of the current directory. I'm currently in opt, so what you see in the highlighted line here is the permission configuration of the opt directory. A double dot means that this addresses the parent directory of the current working directory. As I'm currently in /opt, the parent directory of the current working directory in this case is the root directory, just /. And if you need to take a look at this line, because this line, again, is allowed to read, write, and execute. The group is also root, and the root group is allowed to read, not to write, but to execute. So the question might arise, is the Wölfel user currently in the root group? Let's see. You can find this out by just executing ID. And here you have your user ID. I mean, your user is Wölfel, you should know that. Your user ID is 1000. There is a group Wölfel with the group ID 1000. And then there is a list of all groups that the user Wölfel is assigned to, which is Wölfel, ADM, CD-ROM, sudo. Therefore, I can execute the sudo command, dip, plugdev, lpadmin, lxd, samba share, and docker, but not root. So the Wölfel user is not part of the group, so the group permissions do not apply for the Wölfel user. That means that the last triple of the 9 tuple that control permissions apply for the user Wölfel. So the Wölfel should be considered in regards of world. And the world permissions are read, not execute, not write, and execute. So I do not have the write permission. And because of that, I cannot execute mkdir shared and have it terminate successfully. So I need privileges of the root user. So the root user can be borrowed, so to say, using the privilege delegation method. And the implementation in a Linux distribution is the sudo command. So by writing sudo mkdir shared, whatever comes right to sudo is executed as the root user. I need to enter the password, but then the command terminates successfully. And if we do an ls-lah again, we see the shared directory is created, but as the shared directory was created using sudo, the command was executed under the user root, and therefore the owner and group association with the shared directory is also root. So this shared directory belongs to the user root. By the way, you need execute permissions to change into a directory, period. You need execute permissions to change into a directory. And we have this execute right. So we can, in fact, go into the shared directory, right, as user Wölfel. Just for the sake of showing you that, I will remove from others the execute permission, shared change mod. I will remove the execute permission from the shared directory using this command. And now you see we do not have the execute permission on the shared directory again. And now if I'm trying to go into the directory as user Wölfel, so this is my currently logged in user, then I get a permission denied and I cannot enter a directory because, side note, changing the directory requires execute permissions. So let's reverse this and apply the execute permission for others to the directory shared again, such that Wölfel can go into this. So next step would be creating a file f1.txt. We can do this with touch. Well, the same reason applies here as well. The dot is the current working directory. I do not have the write permission. and therefore I cannot write a file and need sudo privileges. And with sudo privileges, I can do this. And the same reason applies here as well. So we can create the file. It belongs to the group root. It belongs to the user root. And the default permissions are set here, which is everyone can read, but only the owner can write, and no one can execute it because it's a text file, right? Okay, so we have created shared in opt. We have created an empty file, and now, like, the fun begins. Let's write into the file. So from last time, we know that we can use a file redirect, for example, Marco with hello. So this just prints Marco on the console. And because of the lecture last time, we know that this printing is done using the standard outstream. We can redirect the standard outstream using an angle bracket and redirect this into f1.txt. And no surprise, that does not work because we do not have write privileges on f1.txt. The curious thing is that sudo also does not work. Why? And this is a key learning from this task. Sudo does not work because sudo stops at redirects and pipes. So only the echo Marco command is executed under the root user. All pipes and all redirects are not in scope of sudo. So you do not change the user for this redirect or for this pipe. So this redirect is in fact executed using the username of the user where the shell belongs to. And this is the user Wölfel. But you have two options. These two options are mentioned in the task as well. You can use sudo-i in order to change the shell user to the root user. So sudo-i gives you a root shell. So this is the right technical term. And now the shell belongs to root. And we can switch to opt shared, do echo Marco, and then do the redirect. And this works because now this redirect is not executed under the Wölfel user, but under the root user. Root user can write into this file. Everything is good. The second option is you can work with subshells. So we had subshells before. Again, you can in a terminal emulator, what you see is an instance of the bash command or the bash program. But you can execute another shell with an invocation of bash. So inside one bash shell, you can invoke another bash shell. And you can invoke another bash shell. So this is, if you know the movie Inception, this would be bashception. So a bash shell in a bash shell in a bash shell. And what the terminal emulator shows to you is the bash shell that was created last. So let me show this. I have a diagram open here. So when you open the terminal emulator in Ubuntu, you have a bash process. So this is the rectangle in violet color here. And the terminal emulator points to this bash shell that you just opened. But by executing bash inside the shell, you create a second bash process, and the terminal emulator switches to the new created bash shell. So this is basically like this. And if you do this again, create a bash shell in a bash shell the second time, then you create a bash shell in a bash shell in a bash shell, and the terminal emulator shows to you like the most recent bash shell, right? So you can do this. If you type exit, then you terminate the bash shell where you type exit into, and the terminal emulator jumps one back and shows you the bash shell this one, as shown in the diagram. If you execute exit here again, then the terminal emulator, well, will jump to the first bash shell. If you exit this bash shell, let's see what happens there. So, oh, I'm here. Okay. So if I type exit, I jump out of the inner bash shell. If I type exit again, I jump out of the mid bash shell. If I type exit again, the terminal emulator either shows no shell at all or terminates as well. I don't know actually. Let's find this out. It terminates as well. So creating a new terminal emulator. By starting this terminal emulator, a bash shell is created because the terminal emulator needs to show something. And this is how these subshells work. And now what you can do is, let me just go to opt shared. You can enable the -c command. -c stands for comment, command. And if you execute bash-cls, you create a subshell and you pass a single command into the subshell, which is ls. So ls is executed, and then this shell terminates, right? So we do not have an inner shell. If we type exit, should I type exit? I typing exit again to showing you that this bash shell is just alive for this command that you specify in -c. So hitting enter closes it. I have to open it again. So in terms of the diagram, with bash.c, you create a second bash shell. The terminal emulator switches to this inner bash shell. Then ls is executed through this -s option. Here, a little bit bigger. So this is executed in the inner bash shell. Let me connect that. And as the terminal emulator is connected to the inner bash shell, the output of ls is shown in the inner bash shell. And after the ls command finishes, this bash shell also, like, I don't want to have text there, also terminates. The bash shell terminates. The terminal emulator jumps back to the original bash shell and accepts the new command. So this is how it happens. And my drawing skills are exceptional today. And you can use this kind of working in order to do the following. You can now do this under sudo bash.c and provide a command that includes the redirect. So for example, echo Marco and redirect this to f1.txt. What happens here is you create a bash shell, but because you prefix this with sudo, this bash shell is in fact executed under the root user. So you create a subshell that runs under the root user, and with -c, you execute the command echo Marco redirect f1.txt inside that subshell. Password. It works. Taking a look at f1.txt, you have Marco in there, and showing you that this is actually what comes out of the echo command. I cannot include semicolons because semicolon means the end of a command. So this has a special meaning. If I do that and cat F1, you see this is the content of the file. All right, any questions? Then let's talk about package management. Package management, for me personally, is the most difficult chapter in the whole Linux section for one reason. It's not complicated, so it's a little bit complicated. It's confusing in the first place. It's not complicated, so it's not difficult, but it's confusing. And this confusion is the reason why Linux never got into desktop systems. So if we look up the amount of people using Linux on a desktop, well, despite professional users. So Linux on the desktop is still, or has a market share of around 50% for professional software developers and computer scientists, because these are power users and make use out of the shell. But if I consider my parents, or if I consider friends that are not computer scientists, then they would be lost with Linux. Not because it's hard to operate. I mean, you can achieve all the file operations with a graphical user interface as well. You can start program by double clicking on an icon on Linux as well, so similar to Windows. But the major difference, or a major obstacle a regular casual user can fall over is installing software. And installing software on Linux is called package management, because the concept is designed around packages. And it's, again, it's not hard, but it's confusing. Some design decisions, maybe they made sense 20 years ago. Nowadays, they do not make so much sense yet today. So let's see. Package management. What is a package? It's a collection of files that is required to run a software application. So a software application is typically not just a single file that you execute, meaning more complex applications like Photoshop, for example. Photoshop is composed of a lot of components. It's not just the executable that you like execute with a double click. It also loads parts of the programs from libraries. So this library here is a part that includes code like instructions, but a library is not executable standalone. So you cannot double click on a library and run what's inside there. It's a non-standalone executable file that contains like routines or instructions. And executable software applications use libraries in order to do code reuse, right? So sometimes you have the same functionality over and over again. So for example, writing a file is used in program A, in program B, in program C. And you do not want to have like an implementation of reading a file in every of these programs. What you want to do is extract this code that you use for reading a program, for reading a file, into a library, and then load the library in the applications that use this functionality. So this is the concept. And this is employed in basically any complex software applications. So they are composed of executable code, but also use code from libraries. And a package is just a collection of files, and these files can be standalone software applications, libraries, services, configuration files, and such. And the package management system is the tool that handles all these packages. They keep a record of what packages are installed on the system. And this sounds trivial, but we will see it is not trivial at all, because you have different versions and you have like different dependencies. And the dependencies are what makes the whole system a little bit more complex and confusing. So the package management system keeps record, tracks things, keeps all versions of installed packages up to date. So those package updates as well. But let's talk about dependencies, because dependencies are annoying. So one package might use a library that is packaged in another package. So one package might depend on contents of another package. So one package depends on another package. And you can do this in multiple chains. So package A depends on package B, package B depends on package C depends on package D depends on package E, and so on and so forth. So you have chains of dependency relationships. And if you want to just install a simple program, you need to install the dependencies and the dependencies of the dependencies and the dependencies of the dependencies of the dependencies of the dependencies as well. So for a single small application, you would need to install like 20, 30, 40, 50 packages that are dependencies of the one thing that you want to have. And this is complex and confusing. How this works in practice is, you see it on the diagram here. So you're the user, right? So you're on the left-hand side here. And you use a tool which is called the package manager. But what does the package manager do? Primarily, the package manager needs to resolve this dependency hell that is arising there. And the package manager is responsible for downloading the packages from a source. And this source is called repository in this context. So repository is a remote server that is somewhere in the internet. And this repository hosts the packages that you can download. A set of repositories is already predefined when you install a Linux distribution. And the repositories are also distribution specific. So every Linux distribution has its own repository. So if we use Ubuntu, we use the Ubuntu repositories, and we get the packages that are supported by the Ubuntu operating system. If we would use the Red Hat repository, for example, we just could obtain Red Hat packages which are incompatible with Ubuntu packages. So again, confusing. Well, we are Linux, we're using the same kernel, but there are two formats, or many more formats, distribution-specific formats, how packaging is done. Bad idea, but it is how it is. So the package manager contacts a repository and loads the metadata. Metadata is data about data, and in context of packages, the metadata hold, for example, the list of all packages the repository does offer, the versions of the packages, the dependencies of the packages, the maintainer of a package, like a lot of data that describes the packages. This is in the metadata. So when a user wants to install a package, it uses the package manager. The package manager downloads the metadata to the laptop. So this is not done like in real time. So you need to download the metadata first to your computer, and the package manager reads from this metadata all the information on the repository. It has one drawback. It's confusing. Why don't we do this online? I don't know. But the drawback is, if you download the metadata at time A, like today, and you wait a week or two, you have outdated metadata. You need to download this metadata regularly in order to have the most current metadata, because the version is part of the metadata. So in order for the package manager to identify, has the repository a newer version of a package that I want to install, it needs to download the metadata first, because otherwise the metadata is outdated. So updates are missed. And then obviously the repository hosts the packages as well, and also all dependencies. So dependencies of dependencies of dependencies. To make things more confusing, every family of distribution uses its own packaging system. So we use Debian. So we focus on the Debian family because Ubuntu is a derivative of Debian and uses the Debian tools. To add more confusion, there's a high-level package manager and a low-level package manager. So in order for a user to install a software package, basically two tools run. The low-level package manager is Debian package, abbreviated DPKG. So this is an abbreviation for Debian package. A low-level package manager, it's a tool. You can execute that on the shell and the command line. And the low-level package manager can install a package, update a package, and delete a package if the package is there, or if a package can be identified by a URL. So basically, what the high-level package manager does here, the high-level package manager, the only job of the high-level package manager is to interact with the user. So the high-level package manager is a front end to the user. And the high-level package manager does all the communication with the repository. So the high-level package manager reads the metadata. The high-level package manager decides whether or not an update should be done. The high-level package manager resolves all the dependencies. And the low-level package manager only installs packages that are already downloaded or installs packages from a remote URL. So this split up between high-level and low-level package manager applies for Debian, applies for the SUSE family, applies for the Fedora family. I'm using Fedora on my laptop, so I use DNF, for example, and my low-level package manager is RPM. And Arch makes it right, so they have written a tool that does both, right? So can interact with the repository and can install packages. What a revolution here. But as we use Ubuntu, we are stuck with these tools. Yeah, we talked about this. So package management for Debian-based systems used on DPKG and apt advanced package tool is what we as a user use. And we typically, so if we do not do a lot wrong here, we use apt only, and we do not interact with DPKG, but apt is using DPKG as backend. So this is how this works. And we as a user, we can invoke apt, execute apt with different commands. So we can, for example, list all installed packages. We can read the metadata on a package. We can update the metadata with apt update. We can install a package. We can remove a package, and we can update a package. So I will show this to you on the command line here. So test. Let me clear. Oh, clear. So for example, apt list with the option installed. I mistyped installed. Gives me a list of all packages that are installed. Challenge to the chat. What would be the command to count or to get the number of packages that are installed? So basically count. Please put an answer into chat where you say, well, this can be achieved this way. Command, not just parts of a command. Who gives me a command that gives me a list of all installed packages? Ah! Who was first? Oh my, it was, I cannot tell. It was Raman Kazi. So with apt installed list, we get a list of all installed packages. So every package is a line, right? So we pipe this output into the word count, and we want the line counts. And now we see that we have in total 1,745 packages installed in this Ubuntu machine. Is this a big or a small number? It sounds big, right? So let's say 1,800 packages, that's a lot. But if I do the same on my machine, do I need sudo for that? I don't know. DNF list. Oh, installed. Does this work? So actually, I don't know the command for DNF. I only know it for apt. Oh, I guess this will take. Oh, this works. Oh, nice, cool. So DNF list installed lists the packages that I have installed here. If I count it on my system, what number do I get? Dim, dim, dim. Oh, I have to move my head. It's 7,817. So by factor 7, I have more packages installed on my laptop. Obviously, because I have more software installed on my laptop than on this virtual machine. So just that I give you some kind of notion what this means, how many packages, how small and big they are. In general, small packages, I mean, they have a benefit that the content that's in the package can be reused as a dependency on other packages. So the packages are rather small in a Linux distribution. Yeah. Do I have HTOP installed? Yes, I do. So there is I will remove HTOP. So, oops, caps on. Removing packages can be done with apt purge HTOP. Test this. And now I can just remove a package. HTOP was installed before, and now it's uninstalling this package. So I cannot invoke HTOP anymore. I can read the metadata. Apt show HTOP. And this is the metadata on the package. So you see, this is the package is named HTOP. The version is 3.0.5-7 build 2. It's from Ubuntu. The maintainers are the Ubuntu developers. The original maintainer was Daniel Lange. Bug reports can be posted under this forum. And now, interesting, the size of the package is 342 kilobytes. And we all agree that 342 kilobytes, it's not much, right? It's not a huge program. It's a small program. It's 300 kilobytes. But still, this 300 kilobyte program has how many dependencies? 1, 2, 3, 4, 5, 6. It has 6 dependencies. Not counting in the transitive dependencies. So the dependencies of the dependencies of the dependencies. These are just direct dependencies, 6, which is a lot, right? And if you have more complex FFmpeg, more complex programs, then you will see you have dependencies here as well. Well, how many dependencies are these? 1, 2, 3, a little bit more. I don't want to count. But also FFmpeg is again not much. So it's like 2.2 megabytes because it's 2,288 kilobytes. But if I want to install FFmpeg, for example, oh no, let's install HTOP before. So sudo apt install HTOP. You need sudo for installing because this changes the system and therefore you need elevated privileges. With sudo install HTOP, you install one new package, meaning that all the 6 dependencies are already installed on the system, so which is good. So this dependency might be used in other packages as well. And now I can execute HTOP. If you do not know HTOP, it's a tool. It's excluded from the exam, but it's just nice to see how the system resources are used on the command line. So this is my virtual machine. I have 4 cores here. I have 2 GB of RAM, and you see a list of processes that are currently running. So it's a nice and informative tool. So, and now, if I want to install FFmpeg, for example, we have seen like the direct dependencies are not really much, right? So it's, I will count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10-ish. Maybe I missed one, but it's, let's say it's 10. And I want to install FFmpeg, then I get this. Look, 70 newly installed. So my 10 direct dependencies have dependencies of dependencies of dependencies. So in order to run this FFmpeg tool, which is a command line tool to do video encoding, I need 70 packages in total. And instead of 2.2 megabytes, I need 222 megabytes because 70 packages are more in order to install FFmpeg. I won't do it because it takes a long time. But to give you like some feeling how this dependency hell really is in practice. And this is an issue, right? But this is an issue, but this is the way how it works. This was designed some 10, 20 years ago, and we have to live with that right now. So to recap, we have apt commands. So for example, listing, showing, updating, installing, purging, and upgrading. And there's a difference, by the way, between update and upgrade. What apt update does is it downloads the metadata from the repository, updates the metadata, not the packages. Update does not update packages. It updates metadata. Updating the packages is done with apt upgrade. Difference. Confusing, but not complex. It's just confusing. To add more confusion, there's also, there's the apt tool, right? At some like web pages or literature, they use the apt-get tool. And the difference, both apt and apt-get have super cow powers. Wow. And apt-get is a front end to apt. The difference is not much. And this is up to you to research the difference between apt and apt-get, right? Also, again, a level of confusion on top of it. But people have understood that this is complex. There are, in fact, distribution agnostic systems. So packaging systems or package management tools that do not rely on this tool-level approach where you have a high and a low-level package manager and are not specific for a single distribution such as Pacman. But unfortunately, there are multiple tools there as well, and the user base splits up among these tools. So in a perfect world, the community would have decided, well, we solve package management for Linux once and for all. We create a tool that follows the design principles, does this thing very well, and does nothing else. But we ended up with 3 tools. The first one is Snap. Snap is pre-installed on Ubuntu because it's developed and introduced by Canonical. Canonical is the organization responsible for Ubuntu, and Canonical pushes the Snap tool, obviously because they created the tool, so they want users to use Snap. It has an example. It has an example. It has an advantage over just classical package management with apt, because Snap resolves all the dependency hell. So if you install a Snap package, the Snap package encompasses all libraries and dependency that it has. So you install one piece of software and you You just install one package, and all the dependencies are packed into the package. So you do not end up with 70 dependencies, as we have seen in the example of FFmpeg, which is good, I think. But canonical is bad. Not per se, but capitalism is something that you need to have in mind. So maybe you're young persons, and maybe you play a video game after your studies. And maybe you heard about the Unity drama that happened this year. So Unity is a video game engine that a lot of games depend on, right? A dependency, the video game on the video game engine, because it's complex to write a video game engine, right? So they reuse one, but the concept is the same. And the company behind the Unity engine decided to change the pricing model. And not just a little bit, increasing the prices per 10%. They changed the business, the whole pricing model so dramatically that the impact would cause bankruptcy for a large portions of the users. So for them, it's a catastrophe. And this can happen because, well, this tool is owned by this company. So the same story can apply for Canonical, changing the pricing for Ubuntu. And if everything like works around Ubuntu and such, then this is something that can happen to you. By the way, Red Hat did this, I guess, with CentOS. It was not this year, maybe last year. Red Hat made such a move where they changed a licensing model of a software, of a Linux distribution that many people used, and made it basically unusable for these poor users because the license terms did not, or where these license terms were so complex and unfitting that in order to apply to these licenses, a lot of changes need to be done, and users just simply don't use it anymore. So just a side note on be careful when an organization publishes a tool, because things can happen. Flatpak, this is my favorite. This cannot happen if the tool is developed by the open source community, because then it's not owned by a company. And Flatpak is developed by the open source community. It introduces a sandbox idea. So think about like a sandbox that you have in your garden, and kids play in this sandbox but cannot escape this sandbox because this sandbox has like walls around them. So a sandbox ensures isolation for the host system, which is good because a Flatpak also comes with a kind of a container where all the libraries and dependencies is in there. And this container, this bundle, operates within a sandbox, so it cannot cause harm to the rest of your host system. So you have a layer of security, you have a layer of isolation, which is a good thing. The reason why I like Flatpaks is it's easy, right? So like this one package for my software, but it also comes with a marketplace that I like. It's the FlatHub, flathub.com, or is it .org? It's .org. And you can just search for programs that you want to have installed. What is this? Wackerwear, for example, a WhatsApp client, or Thunderbird is a famous one, like a mail client that you can install. Steam, if you're a gamer, you can download and install Steam pretty quickly. You can install OBS Studio quickly. You can what is also like a program like GIMP is a program where you can do photo editing and such, and you can just search in the marketplace. If you have Flatpak installed on your system, you can press this install button and then you install the package, right? So this is what you want. You want to search for software, you want an install button, and then you just want to launch and work with this software, right? This is what we users want. Flatpak gets you this. Open source, so no fear of capitalism, sandbox, all the dependencies in there, fine. And the last one that I want to mention is AppImage. AppImage follows a one application for file paradigm. It is basically copied by macOS because macOS has the same as well. So from the Mac users in the audience, when you install a software, well, you download like this bundle, and it basically it's a bundle, but it is encapsulated as a single file, and you can just double click on this single file, and you can move this single file in an application directory, for example. So it adds a level of quality of life to software installment. It's nice. AppImage does not have sandboxes. AppImages does encompass necessary library and dependencies, uses this one application per file paradigm, and does not require sudo privilege. I guess Flatpaks do, maybe. I have to find out. But the thing is, in practice, some AppImages are packaged poorly, and maybe it's just my subjective opinion and my previous experiences with AppImages. My experience is AppImages, there's a risk that this AppImage does not work because it was packaged badly. Flatpaks, on the other hand, I never had a Flatpak that did not work. And the community also is moving towards Flatpak, right? So we have these three systems now. The community was undecided a year or 2 or 3 ago, but also subjective. For me, it feels like the community is moving to Flatpak. Also my recommendation. There's an assignment, and we do this assignment before we go to the terminal editors. So let's see. Software packages. As we are running out of time, let's do the whole Flatpak thing as homework. So we start with this the next time. And you do, without a breakout room, because everyone should be able to install a package. We saw HTOP before, and the task is just doing an install with apt, install the program HTOP with apt, download the metadata before, install it, then run the HTOP program and exit. I guess you need 5 to 7 minutes for that, adding 15 minutes for the break that we do on 11:15 makes me thinking, let's talk in 25 minutes again, including the break, and then we continue with our next section, which will be terminal emulators. Is anyone having a question? That's a no. So talk to you again in 25 minutes. Both are not that comprehensive. But there is a key insight in terminal editors, and you need to know that because this is essential. There are 2 terminal editors that are dominant in Linux shells. The first one is Vim, the second one is Nano. Vim being the successor to a very famous editor called VI, so it's just a letter more. And Vim is one of the most powerful code editors that you will ever experience. But with this power comes complexity. So I'm using Vim for basically anything. I use it as a regular text editor. I use it for coding. When I'm using an IDE to program something, I always have Vim plugins in there because I'm very used to the shortcut that Vim provides, which makes me editing text very fast. If you want to master the art of Vim as well, there's a great video series on YouTube that I linked here from the Primeagen. Is this pronounced correctly? Anyhow, this guy made an exceptionally good YouTube series for different levels of experience with Vim. If you want to go that rabbit hole and want to be the fastest code editor on the planet, you should see this video. The Vim command just is used to start the editor, and without going into the details of Vim, because there are different navigation and selecting concepts, I guess 2 or 3 key insights are important there. The first one is that Vim has modes. So there is a normal mode, which is used for navigation. There's an insert mode that is used for manipulating text. And there's a visual mode that we do not take into consideration in this course, but it is used to select chunks of text that to be manipulated. So moving, for example, a source code functions from top to bottom, this is done in visual mode. And regardless of the mode you are in, you can press escape to fall back to normal mode again. So you can be in insert mode, you can be in visual mode, press escape to go to the normal mode. And now it comes. So if you're in normal mode in Vim and you want to add text or modify the text, you need to press the key I before to change from normal mode to insert mode. And then you can navigate using your keyboard and the arrow keys. And when you're done with the editing, you can insert the commands :W, which writes the changes to the disk, :Q for exiting the editor, :WQ to save and execute the editor. Oh, I need to see if I have Vim installed on my virtual machine, but I guess I have. Let's switch to my working directory. Let's go to the downloads directory. I guess I have a file there, yeah, favorites.txt. So you use Vim, this terminal editor, by just Vim and then the file name that you want to have. If you want to create a file, you can new file. You can just write the new file name after Vim, and then the Vim editor opens up. But you are not able to insert text in it, right? So you need to switch to insert mode first in order to write some text. You see it, I'm switching to insert mode, I'm switching back. Insert mode, back, insert mode, back. You see the insert mode is indicated on the left bottom corner of the terminal editor. And if you're in insert mode, hello class, this is Vim. I hope you enjoy it. Once you are done, you press escape. And this is the most important key insight. I had this as an exam question the last term. The question was, how do you close the Vim editor? And the answer is you need to write a colon, and you see it on the bottom left. Then you write WQ, which writes and which closes the editor. This is important because other tools might use Vim or its predecessor VI. It's installed as well. Oh no, VI points to Vim. That's interesting. But anyhow, some tools, if they want you to edit text, they sometimes default to VI or Vim. And you need to know how to edit text in Vim, and you need to know how to close the editor. And you know it now, because you know there's an insert mode, there's a normal mode, and you know we write WQ prefix with a colon in order to exit the tool. Git, for example, it's a very famous tool. You will use it all the time, starting from the second semester across your professional life. Git is one of the essential core tools of every computer scientist. It defaults to Vim when it comes to opening editors for commit messages. This is the reason why you know it, or you have to know it. In the beginning, I would not recommend Vim, even if I use it myself, and I'm praising Vim. Vim is the most powerful tool, and you are very fast with Vim. It's complicated but powerful. In order to really master Vim, you need weeks, months, even years. So if you are down the Vim rabbit hole for 2 years, you outperform anyone else in writing, but it takes a long time. In the meantime, you can use Nano. In Nano, you can also like navigate with arrow keys, and it has like a more intuitive user interface. So this is how Nano looks like. So you can use the arrow keys to navigate around there. It does not have any modes, so you use like delete and use your keystrokes to enter text. So this is like a more native, intuitive style of editing. And exiting, it's hinted as in the menu below. So you cannot use the mouse because this is a terminal emulator, but Control X, you can exit it, write the file name, and this is how you use Nano. Yeah, easy navigation, no change of modes, pretty simple. Control X save and exit, and exiting the editor. And this is it for the shortest subsection of beginning with Linux, but still the key insight is Vim defaults in some distributions, insert mode to insert, WQ to save and exit. Questions? Okay. Then the last subsection, it's about scripting. It's also not complicated, it's not long. A script is a text file, and you can put in this text file a sequence of commands for the shell to execute. Because what we know so far is, well, we have commands. These commands do one thing well. We can achieve more complicated tasks using a chain of commands. But these commands then, especially if we chain them together, get complex. There are a lot of options, there are a lot of arguments, there are pipes that you need to care about. So it's in general a good idea to store these commands somewhere safe and suitable. And the best way to do this is a shell script. As it says here, it's a text file that you can edit with Nano or Vim. And you put a sequence of commands in this text file, and you can execute this text file, and the commands are executed from top to bottom. So like in programming, but it's not really programming, it's scripting. And this makes you very efficient. So I'm doing shell scripting all the time. And it's very efficient for repetitive tasks. A shell script does not need to be super clean. It does not need to be like created very elegantly. So, I mean, when you program Java, elegancy is a goal that you aim for. But a shell script is like a dirty text file, and the shell script needs to get a job done. It's very good for a task requiring multiple commands. Script can streamline the process. You can automate this. And the rule of thumb, this applies for any automation techniques. If a task is repeated more than 3 times, consider scripting it. Let's take a look at some shell scripts. Oh, there's a question, what is Vim used for? Really? I demonstrated Vim, and I talked about Vim 10 minutes, I guess. So, wake up. This is a shell script. This is a rule, a shell script always starts with this line. similar in each shell script. This line is called the shebang. It's always a hashtag and an exclamation mark, and then it defines the shell that should be used when executing the script. If we want our commands to be executed in a bash script, which is our default and also the default in the Linux distribution, we write / here in order to tell the shell that's executing the script that this is a script that should be executed in a bash shell, because there are many shells. There's a Z shell, there's the S shell, there's just the Bourne shell, which is the SH shell. So there are multiple shells, and you can execute a script that was written for Z shell, for example, on a bash shell. This is possible, but then you need to specify that this script, what is following in the lines after, are written in Z shell syntax. What you see in line 2 and 3 are comments. So comments are like, as for programming, they add documentationary value to the script. So if there is something very complex and you have the idea in your mind, write it down as a comment for your future you to remember what this script does. And this applies for bash scripts especially because the commands can get quite complex and sometimes it's difficult to read them. Like with source code, you can, if you gain experience and seniority, you can make sense out of source code by just looking at the source code. But making sense out of very complex scripts is a different story. So comments especially important in a shell script. But this script is simple. This executes just the date command and the who command in sequence. So first executes date, then executes who, and then terminates. You need the execute flag on shell scripts because otherwise you cannot execute it. And there are two ways to execute it. You can execute it in the shell that's currently running. Then you need to use the syntax that you see on line 1 here. So point / script name, or you can execute it in a subshell where you just bash script sh. You write that down, it creates a bash subshell, executes the script inside that bash shell, and then terminates once the script is finished. Best practice, by the way, always use the .sh file extension, even for bash scripts. So .sh comes from just the Bourne shell, the sh shell, but it also applies for any other shells. So use it for bash shells, use it for Z shells, use it for S shells, in order to indicate that the content of this file is a shell script. You can have variables in shell scripts. So starting from line 3, line 1 is the shebang again, line 2 is a comment, line 3 defines a variable. It works the same way as environment variables work. So you assign symbols, names, variables, days in this example, and with the equality operator, you assign the value. Be aware that there is no white space between the variable name and its value, and it would not work if there would be a white space. The concept of data types does exist in scripts, but they are not stated and declared explicitly. So this 10 is in fact an integer 10, and this string London Redford is in fact of data type string that you assign to the variable guest in line 4. With the $ operator, you can reference values for variables. So in order to get the value for guest, you write $guest and you get back the value of the variable guest. Then, yeah, again, you can reassign values to variables. Here in this example, we assign 5 to days, we assign Dakota Puddle to guest, and then execute this. You can have functions. Concept is the same as you know from programming 1. So, and I guess you're doing Java, and functions in Java are called methods, but it's the same concept. In shell scripting, they're called functions. So you can declare functions / methods, and in the body, of this function, you can add a sequence of shell commands that you want to execute. And if you want to repetitively execute the same sequence in a function, you can use functions for doing that. One thing to mention, in Java, you're used to having input parameters defined in the signature of the function, meaning in these two parentheses here. In Bash, we use positional parameters, where you can pass parameters to the function, and you can address these parameters using the position, like $1 refers to the first argument that you pass, $2 to the second, $4 to the fourth, and so on and so forth. So passing arguments to a function is not based on input arguments, as you are used to in Java. It's based on positional parameters. In lines 5 and 6, you see an invocation of this function here. So basically, you write the function name, and you provide the arguments to the function just as the arguments to this command as you would have done it on a bash shell. So if you pass this string chi to the function greet, this $1 resolves to the first argument that you provide to the function, and this resolves then to chi. In this case, it's Ben. $0 is a special positional parameter, and it represents the script's name. So we start with counting for arguments that you actually pass to the function by 1, and $0 always holds the script's name. The same approach works for not for function arguments, but for script arguments as well. So let's take a look at this very simple 3-line script. First shebang, then we have a comment, and then we have just an echo command. And the echo command just prints out, hello $1, glad to meet you. And if you provide an argument to the script, then this first argument is held in $1, and the output would be, hello Andreas, glad to meet you. Bash scripting is Turing complete, meaning it can calculate everything a general purpose language can do as well. So you can create the same programs in Bash scripting as you can do in Java. But a Bash script is maybe not the right tool for a very sophisticated program. But still, you can achieve a lot with Bash scripting. And there are further structures that are worth mentioning, but we will not cover it in this small Linux crash course. You can have loops in scripting. You can have control structures such as if then else. You can have what else? You can have a lot of things, right? If you want to read further, please take a look in the book that is referenced by the number 3 on iLearn. Let me look that up for you. Oops. It's this. Oh, it's an organization. Let's take a look in organization. Here we have the literature list. Guess it's at the end. Yeah, 3. So this is the Mastering Linux System Administration book from Breschanan et al. And you can do further readings on shell scripting there. But the content of this chapter ends here. Of course, with a small assignment. Let's take a look at it. Let's go out of edit mode and take a look at the scripting task. 3 parts. Part 1, we do it right now. Part 2 for you as homework. Part 3 for you as homework as well. But this is in fact optional. I will declare it as optional. Give me a second. And in the meantime, I explain to you what optional means. Optional means that it is, oops, it's not optional, that it's not exam relevant. So whenever something is flagged as excursus or as optional, this is an indicator for you that this is something that I recommend you doing, but this is not relevant for the exam. So there will be no exam question regarding VirtualBox guest add-ons, but it's still recommended to do so. On the other hand, if there is something declared as homework and it's not optional, this is in scope of the exam. So you should download, execute, and study the sample script from the lectures in order to understand how the scripting works. And this way, like, improve your skills in shell scripting. And this is my expectation that you know this kind of material, subjects, stuff, materials for the exam. But we do logging random numbers today, and we use breakout rooms for these because here collaboration in fact makes sense. Let me recreate all rooms. You will be mixed together as again. I will enable design automatically. So I guess you are assigned randomly. And you do part one, logging random numbers. So you write a shell script that displays a random number on the screen and generates a system log message with that number. There are hints how you can get random numbers. There is a hint how you can use the logger and the options. Yeah, basically all the instructions are there. So for that, I give you 20 minutes, meet and exchange, talk to each other, and together solve this logging random numbers task. Before I open up all the rooms, is there any question? That's a no. Then talk to you in 20 minutes. The rooms are open right now. Yeah, people are coming in. So the task is to learn about two things. We have an environment variable. It's called random. I need to echo it out. Otherwise, it would be interpreted as a command. And as the command random number does not exist, we get this error message here. So if we echo random, we get a random number. Do it again, 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 and so on and so forth. So with echo random, if we echo it out, we get the random number on the console printed out. Okay, and this is the first thing, learning about the random environment variable. The next thing is the var log subdirectory. When I'm LSing this real quick, oh, this is illustrated. Can I make it? Yeah, I mean, you can see it. Can I make it full screen to look? Yeah, this looks better. So this is the content of the /var/log directory on the distribution. And you see we have a lot of logs there. For example, we have the authorization log, we have the boot logs, we have the kind of system logs with a D message, we have the log of D package. So logs regarding package management. We talked about package management before. There is the CPU manager log, for example. We have the Ubuntu Advantage log. I don't know what this is, but we have the syslog here. The syslog is the important one because the syslog keeps the system logs. And if we cat the syslog, we see the contents of the syslog. So do we have something interesting here? I don't know. So a lot of messages are in the syslogs. If something goes wrong and you are tasked to troubleshoot the system, this is the starting point where you conduct your investigation, taking a look at the system logs. Maybe there is an error in there. Question to the chat. What would you do in order to search for errors in the system log? You got a minute. Dum 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 dum. Do 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 dum 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 dum. Unfortunately, no one has the correct approach. Kero tried with standard error. Well, yes, Arma has a nice idea. Well done. So standard error does not work here because standard error is a stream of a process and has nothing to do with like text processing on the command line. Arma has the right idea. We can use the grep tool because grep filters lines according to keywords that match on the line. So if we want to search for errors in the syslog, we can just grep for the term error in the syslog, and then we see all the lines where error is inside. So what do we have here? SQLite errors. Database disk images malformed. Okay. Then a kernel error, command buffer header error. And what do we have here as well? I mean, these errors, I guess, are not critical because my machine is still running with these errors. But still, if something does not work as you want to have it, take a look at the syslog grep for errors, and you can find a starting point for your investigation there. So, but the task was, I'm going back to my home directory and clear my shell out. The task was to implement a script that prints out, well, let's read it, that displays a random number on the screen and also generates a syslog message with that number. So let's do this. I'm using Vim because I'm used to Vim. So random.sh. I will create a file random.sh, go to insert mode, and then start my shell script. Before you even thinking about starting scripting, the first thing that you do is you write the shebang, bin bash. This is the first thing. Then the sequence of commands that you want to execute. So we want to have a random number on the line. We know that we can do echo $random then. And maybe I go out of the editor. There is a tool called Logger. And if you enable user.info, I guess was the option, and provide a message as the second or as the first argument. -p user info is an option, so it's not an argument. So the first argument is hello world. If you write this and you cat the syslog again, oh, syslog is it's the last one. I mean, I almost did not see the log, but this is the log entry that you get, the hello world from the user Wölfel on the machine OS NVM. So this works out. I recently found out last week that this this -p option is in fact optional. So you can just do logger hello world, and you have the first hello world is here and the second hello world is there. And you see things are, I don't know, it's the last one. But this is fine. This is fine. So but this is the way how we can create log messages. So back to my script and opening Vim. So I can use logger and do a random message there. Question to chat. Why does this script, or what is the error? What is the mistake that I'm making here when I'm doing this kind of script? Exactly. Rahman has the right answer. We have two random numbers there. So an option here is to create a variable where we assign the random number 2. And we use the value of this variable in both the echo and the logger command. Then we need to make it executable, because otherwise, you see, random.sh. If I want to execute this the script, I cannot. Showing it again, I cannot because where's my? I'm gripping for it. Because this is the file random.sh. We do not have an execute flag on this text file. So with chmod plus x random.sh, see, now we have the execute flag here on the owner, on the group, and on others. Now can execute random.sh, and we got 7,214 as my random number. And I have it in the log file as well. So this works out perfectly. I have prepared a script, my random, to show you in order or to show you the function approach, because this is the last task that we need to do in this kind of exercise. So here you see a function, gen random, and we do the same approach as we saw before. So we assign a random number to a variable, myrand, we echo this out, and we use the logger tool in order to get it in the log. We execute it 3 times. So this short sequence of 3 commands are executed 3 times in a row. So basically 3 times 3, 9 commands that are executed on the shell. Okay. This is it for the task. Any questions? Then let's switch over to my slide deck. Oh, this is a wrong one. Let me share this deck, because we are changing to memory management. Amar, the logger is a tool that you can use in order to put a message into the system log. This is how this tool works. In the last half an hour, let's talk about memory management, and I hope we come to a point where we can start the next time or discuss the next time. So memory management, maybe you know this guy. This is Bill Gates. Bill Gates is famous nowadays for a lot of conspiracy theories, putting chips into brains and such. But no worries, Bill Gates is a computer scientist, the pioneer of operating systems, the former boss, the founder of Microsoft. Everyone knows Microsoft, and Bill Gates is one of the richest persons on earth. He was for a long time the richest person on earth, but I don't know who's the richest person right now. Is I guess Elon Musk is thrown off the throne because of his Twitter acquisition. So I don't know, but Bill Gates is also famous for a quote: 640K, which means kilobytes, ought to be enough for everybody. 640 kilobytes of memory should be anything for everyone. And this did not age well. You should tell Chrome that half a megabyte is enough for a memory for you. So this does not apply today anymore. So today, typically we have, I guess standard is still 8 gigabytes of RAM. Some people have notebooks with or machines with 16. Power users opt in for 32 gigabytes of RAM, but 32 gigabytes of RAM in like a consumer machine should be enough. Should really be enough for now. What we are starting the chapter off is a very basic concept that applies for a lot of scenarios. It's caching. Maybe you heard about it. Caching means, or a cache is not like a box where you can find loot in. So all related to computer science. Cache, but this is also cache. Why does my deck not work anymore? Something is broken. Let me restart this quickly. Oh no, you cannot see my browser. I guess what's happening? Anyhow, let's switch over to slides. Anyhow, cache is a hardware or software used to store data temporarily in a computing context. So the context is computer science. And it's used to make memory access faster. And this can happen on a lot of levels. You can make RAM access faster, so primary memory. You can make secondary memory access, so accessing an SSD, for example, faster. The concept is always the same. We use a small amount of faster, more expensive memory, because the higher you go up the hierarchy, right? So creating registers is more expensive than creating RAM, because they lie right next to the CPU, inside the CPU, next to the ALU. And it's more expensive to have RAM than to have like a hard drive. So we use a small amount of faster, more expensive memory, and we do something that is illustrated here on the right-hand side. So this is a scenario where we speed up register RAM access, not register access, RAM access in order to fetch instructions. Because again, a program is a sequence of instructions. Program is stored basically on a hard drive. Then it's loaded into RAM. When you double-click execute a program, then it's loaded into RAM. And from RAM, the CPU, the control unit of the CPU, fetches the instructions in a pipelined fashion. But this RAM access is way slower than a register access. So to speed this RAM access up in order to execute a program more efficiently, we use caches. And this works as follows. The CPU, when it wants to load an address from RAM, it first checks if the value that we are looking for is in the cache. The cache is faster, more expensive than RAM, but is not as big as RAM, right? We have a small amount of faster, more expensive memory. And if we find the information in the cache that we want, then we are happy, right? The CPU can use it. If we do not find the information, like the value of an address in cache, we go the conventional way and we load it from RAM. But then, once we loaded something from the conventional way, we put it into cache such that for the next time we can load it from cache instead of RAM. And you only keep informations that you require more frequently. So addresses that you access in a high frequency, this is what you want to have in the cache. And things that you rarely use, you do not want them in the cache because they take up space. Cache is a small amount, so it's smaller than memory, so you cannot store infinite amount of information in there. So you just want to store the information that you really need, and these are the high frequent used addresses. Used in disks, CPUs, operating system operations, network accessing, you use caching systems as well, and they significantly, it's not a small improvement, they significantly reduce data access and latency times. A CPU or a world without caching would be way, 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 way slower than we are used to it right now. Yeah, a cache client checks the cache first when trying to access data. We call it a cache hit if we find the information in the cache, and otherwise we call it a cache miss. On a cache hit, you directly take it from the cache. On a miss, you fetch it the conventional way and store it in the cache. And the last bullet is an important one because this is one important question that applies to caches and applies to main memory as well, and is one of the main concepts that we want to talk about in memory management. Like when the cache is full, how do we select an information that we throw out of the cache in order to make space for something new? It's called data eviction. So when a cache or a memory is full, how can we decide what we throw out? This is a very non-trivial question, and we will talk about these algorithms later. I guess not today, but this will be the main topic of next time. For the CPU, we have three different caches. We have the level 1 cache, L1 cache. It's integrated within the CPU core. So it's in the core, not next to it, it's in the core. It's a little bit far away than the register. And this is the cache optimized for frequent and recent instructions and data access. We have a level 2 cache, which is still allocated per core, but it's not in the core, it's next to the core. So like physically next to the core. And it is used to make main memory referencing more quicker. So the first one is just for instructions and data for these instructions, so operands. The level 2 cache is for general purpose main memory references. And then we have level 3 cache. And this is important because it addresses what we call the cache coherence problem. Each of the level 1 and level 2 caches is allocated per core. And if we have a 16-core CPU, we have 16 level 1 caches, and we have 16 level 2 caches. But what if, no, before I come to the what if, this also means that we have information that was loaded from RAM and is in 16 separate caches. The same information in 16 separate caches for a 16-core CPU. So what if the information changes, like the value of an address changes, and the change in this information means that the cached values are outdated. So you change something in memory, which invalidates the value in cache, right? And you do have invalid values in 16 caches. Or if one CPU core changes the value in memory and in the cache, you have one valid cache, but 15 outdated caches. And this is what we call the cache coherence problem. And what we want is consistency across all cache copies of a memory location. So one memory location, the value should be valid, should be consistent across all like caches that we have. So this is targeted in level 2 cache here. If it's an instruction, this also applies for level 1 cache. But this level 3 cache is memory on the CPU package. So it's not allocated per core, it's allocated per CPU package. And it is used to solve the cache coherence problem, which we will not address in detail. We just mention it. And the important information is that level 3 cache, it's not per core, and it does not make things faster. It just addresses the cache coherence problem in a multi-core CPU. Here we have an illustration on the right-hand side, and also we have values. We have values for access times and slightly outdated Intel 14th gen. Right now, it was, I guess, published 2 weeks ago, if I'm not mistaken. But the 14th generation is basically the 13th generation with a little higher CPU clock. So values for level 1 cache, level 2 cache, and level 3 cache are still the same for the most recent generation of the Core I series. So this is actually valid information and state of the art. We have 80 kilobytes level 1 cache per core, which is not much, like 80 kilobytes, right? compared to main memory, which is in the gigabytes range. We have 2 megabytes level 2 cache for each core, and for level 3 cache, we have 36 megabytes shared. So you see it on the diagram. We have registers. We calculated the access speed of registers with the newest generation CPU cores, which is in the 200 picoseconds range. So, and level 1 cache access of 1 nanoseconds is still way faster than the at least 20 nanoseconds that we have in RAM. So a factor here is 20. It's huge, huge. So imagine that RAM access in 80% of the time is 20 times slower. This would have an insane impact. Level 2 cache 2 nanoseconds, level 3 cache 6 nanoseconds. So you have like a notion on how fast things happen there. And this is it for caches, right? So a very simple concept, simple, but I say it again, hugely effective. Anyone a question regarding caches? Does cache affect the speed of browsing? Yes, it does. It does. Excellent example. Thank you for that. In this example, right, RAM would be like a remote server where the website is stored. CPU would be your browser, so this would be the cache client, and the browser would have like a cache, and what's inside the cache is are resources that you have already fetched once. For example, images. So if you load an image from a website and you visit the website again and again and again, you do not load the image every time you visit the website. The image is then in the cache, which lowers the volume of data that you need to transfer over the network. And to answer your question, this has a great impact on network performance and browsing performance. So the answer is yes. Address spaces. I want to talk about address spaces, even if the time is progressing right now. But this is the main concept of next week's session, and I want to set the stage for next week. And I want to talk about physical memory. So we know we have programs. Programs are instantiated as processes, and you can have multiple processes of the same program. So I can start my Chrome browser 5 times, 5 instances, 5 processes of the same program Chrome. Okay. And there are issues with these processes having direct access to physical memory for mainly 2 reasons. You can read one of them on the slide here. If a process has direct access to physical memory, like addressing physical memory, the process could write into memory regions that this process is not supposed to do. For example, into kernel space. Right? In kernel space, all the instructions of the operating system resides. And if a process can change these instructions of the operating system, it can compromise the operating system and doing all kinds of shenanigans, like making the system crash, stealing secrets from another user. So for example, there's a user logged in doing online banking. If you could read physical memory, you could read like sensitive information of another user's session, right? The second issue is that processes can interact with each other and can have an impact on each other. So imagine a program, Chrome, and Chrome is programmed to access the address 28 hex in main memory. If you have multiple processes of this program, multiple instances want to access physical memory address 28 in hex. So they can interfere with each other depending on their programming. If the programming is read a value from address 28, you have multiple instances, then you have multiple processes that are competing for accessing memory address 28. This is an issue. So concurrent execution of multiple programs is problematic because they interfere with each other. And the question is, how can we solve this pickle? And the answer is address spaces. So a process never has access to physical memory. And what the operating system provides a process is an illusion of physical memory, which we call logical memory. And the address space of this illusion of logical memory is called an address space. It's the range of addresses a process can use to access memory. So in fact, the operating system creates an address space for process A, creates an address space for process B. And these two processes only operate in their own illusion of an address space that can have the same range, like the range from, let's say, 0 to 5,000, to make it simple. And in our example, where we have two processes that address the same address, access the same address, then now they do it in their own address space. And the operating system in the back, behind the curtain, remaps the addresses in the virtual address space of a process to something physical. So the information needs to be stored somewhere, right? So this is in physical memory. But the operating system is under control of the physical memory and maps addresses from the address space of a process to physical memory. Every process has this distinct address space. It isolates these processes. They cannot interfere with each other because every process has its own address space. And it's managed by the operating system. Does the mapping of addresses used in a virtual address space. These addresses are mapped to physical memory locations. And in our example where we had this 28 address in one program, or when it's programmed here, it maps to a different physical location when this is instantiated in multiple programs. So this is the idea, the main idea. But in order to make this work, a lot of things might happen. And the first thing that you can do is you can relocate. Relocation refers to the translation process of a virtual address, which is in the address space of a process, to the actual physical address, which resides in main memory. Operating system does that. And this is also the mechanism that we use in order to realize multi-programming. So if you remember the first or the second lecture that we had, one of the first concepts that were in the history of operating systems was multi-programming, like switching between programmings based on their I/O behavior. And one question that arises in this context, well, how can these programs access memory when they are in different locations of memory? Because the sequences of instructions hard code the memory address. How can this work? What's typically employed there is called dynamic relocation. Dynamic because it happens at runtime. There is also static relocation, but no one uses static relocation anymore. So in dynamic relocation, we use two hardware registers, which we conceptually call base and limit. And these two registers define a range of memory a process resides in. And this is like consecutive memory segment. I do have a example right away. So when a process wants to reference memory, for example, address 28, we add the base value onto each memory reference, each memory access. So we basically shift every access based by an offset that is defined by the value of the base register. If we exceed the limit, then the operating system knows, well, this is a bad memory access, and then I guess it terminates the process then. The example here. So for example, we have two processes, process A and process B. Each of the processes has registers, base and limit. Base means this is where it starts, where the memory segment is the memory segment ends. So process A ranges from address 0 to address 3 FFC. So this is just a hexadecimal number. Process B, on the other hand, starts at a base address 4000 and ranges up to 7FF8. And here below you have the programs. You have addresses hard-coded in there, right? So this jump instruction or this jump instruction says, well, jump to address 8 or jump to address 0, right? But as process B, or whenever this instruction is read and this memory address is found, the operating system or the CPU, it's implemented in hardware, adds the base value on top of these addresses. Because here you see the physical memory, right? So process B shifts up, starts at 4000, ends here. And when this physical memory, this instruction is executed, we add 4000 to it, and we start right here. So it's basically shifted by an offset above or below, depending. The thing is, to conclude, this is how you place multiple programs in a single physical memory, and this is how you realize address spaces, or you can realize address spaces, because the address space of process B would be the green thing, and the address space of process A would be the blue thing. And with these two registers, you can perform the shift, and this creates the illusion for these programs. This all start at the bottom, and they have like memory available. The last concept that we talk about today is swapping. And swapping is a method that is still employed today. And it addresses the question, well, if my main memory is full, what do we do in order to make some space? So it's a strategy to deal with memory overload. And what we want is we want idle processes to be stored mostly on disk and not keep space in the main memory. And we want to do two operations, swapping in and swapping out. So we have two operations in swapping. Like when we have the question, our physical memory is full, what do we remove from physical memory in order to make space for another process? Then we want to swap out a process. This means writing the address space to disk and removing it from memory. And we want to swap in the new program, like reading the address space from disk and loading into memory. These two operations are possible. Throwing something out and getting something in. Technical terms, swap out, swap in. And there are different algorithms for any of these two operations. So how do we decide which process to swap out? And how do we decide which process to swap in? When taking a look at the clock, we will stop here. And we start from next time when we talk about swapping and the impact on these kind of decisions on the operating system. Does anyone have a question? No, then we conclude for today. Thank you very much for attending and talk to you next time. Have a nice rest of the week. Bye bye.